So in my talk today, what makes this continent super is a talk most about the doubts I have than anything that I can tell you really. And so I'm going to start just asking the questions I ask all the time. And in fact, I hope after that I learn more than you do, because I have truly a lot of doubts about it. So let's see if it works. So first, I'm going to start with a program of what I'm going to take in this presentation is like, what makes a continent just large and what makes a continent super continent. There should be some sort of difference, and I will go about what some people think or what I think. Then I was like a cycle to rule them all, and how people has evolved the ideas about what is the supercontinent cycle and how that is the influence of being large or super on that continent. And then I will go a little bit on my favorite topic, which is Pangea, and the ideas that I got from the supercontinent cycle, thinking about Pangea, which usually is considered like, you know, the supercontinent that everybody knows, or the one that we are sure about. And finally, I will go to the conclusions. Large or super, all the talk is going to be every now and then punctuated by albums from some bands that have names of supercontinents. Some of them are terrible. I have listened to all of them. I do not really recommend to look for them. Usually they are just nerds that are geologists trying to make something fun, but it doesn't really work. But anyway, this is one of the best, in fact, the Rodinia album. So what makes a continent large or just super? And just using a little bit the idea of making memes with the IKEA instructions to form one. Yeah, we have some continents, some plates, and we just want to assemble together to make a supercontinent. But it's all these plates together will make a supercontinent. In fact, the ones that I have there would make some sort of Gondwana that, as we have seen, there is a pretty much some doubts about if this is a supercontinent or only one part of Gondwana was a supercontinent. Sometime last week, there was that debate on this seminar series or these papers in the latest volume of the Geological Society of the London special volume. So in the classical definitions of supercontinent is like Paul Hoffman's definition, like the majority of continents altogether. Sure, that's a simple, conceptually free definition. It's not quantitative. It's useful. You can say it's a supercontinent because only a couple of them were not there. Or there is GeoMerit, which is quantitative, said 75% of the, you know, it's a clear boundary. I'm still doubting if 74.7 makes not a supercontinent, but 75.2, it's a supercontinent. Obviously, he was not thinking about it as like 3/4, roughly. But still, it looks arbitrary, like why 75? In the case of Paul Hoffman, why the majority? The majority of the supercontinents in an Earth with a few minor plates, really small, will make still a continent pretty small. Like when we think about this Precambrian, supercontinent, Archean or Polyproterozoic, and they call it supercontinents, or some people call it supercratons or things like that. The size of that sometimes will be pretty small. So why the majority of these smaller continents make super and not Africa, for example? Yeah, to me, that is a doubt. This is pretty arbitrary. In fact, I was wondering, is this just a supercontinent? So this is a map, just a different projection, but it's a map of the Earth today. And basically, you could walk at some moment from, especially during the glacial periods, you can walk from South Africa to South America all along, just with the exceptions of Australia and Antarctica. All the continents are technically together. I think we agree that this is not what we used to call a supercontinent, but still, it would be just all land masses together. So all land masses together doesn't make a supercontinent, or what we think is that this is not a supercontinent. So then I started thinking, if this is not, why others should be? That okay, maybe because this is we can think there is a tectonic thing. These continents, in fact, are separating in many cases. There is tectonic activity, and I thought, okay, so maybe a supercontinent is a superplate. And this is the definition I coined myself, but just to myself. I didn't pretend to be like the new definition of supercontinent, but it's to myself. I think a supercontinent, then it should be a single plate. So it would be a large continental plate. Otherwise, there is not much difference on today continental scheme or any other. If the plates are interacting either by extension or by contraction, they're still two different plates, and it is like right now. So my definition, to me, and what I think most of the people is thinking, is that a supercontinent is a single continental plate. It's a superplate. And then I thought, if it is a tectonic definition, maybe it's capable of influencing the mantle convection or patterns or some other stuff. That does not need to be true. In fact, I will go a little bit after to that. And in many cases, people think it is, but it could not be, and it would be still okay. The thing is that for the supercontinents, and besides the case of Pangaea, we only have proxies. Yeah, well, there are some kinematic, some plate kinematics that we know, but from the Jurassic, plate kinematics are sketchy because we don't have seafloor, and from everything pre-Carboniferous gets really sketchy. I mean, paleomagnetism is poor. Sometimes poles are for 50 million years, which, well, yeah, we are geologists and we don't mind having this error margin sometimes because it's hard to get data. But yeah, in 50 million years, India was almost in the other side of the world. So it's difficult to just assume this pole is really valid for such a long period of time. The amount of record we have is scarce sometimes, especially the older we get, it's really scarce. But, you know, the good thing of geology is there are always some proof. So, for example, here in the, can you see the pointer?
Yes.
Okay. So here in the figure in the right is the, you know, the origins, collisions, and large igneous provinces, and people has used these as a proxy of supercontinents. If this is the case, if we use the number of origins, for example, or the development of large igneous provinces as a proof for a supercontinent, then we have to go exactly to a definition that includes tectonics, not only a superplate, but also that has some influence. If it is only origins, it could be just plate tectonic. Yeah, we are just getting all together at some moment. But if it is having some influence in large igneous provinces, then it's something else. It's not just randomly the continents got together once and that's it. But still, yeah, there are some periods of time that there are more origins or less origins, and people have used them as a proxy. Yeah, if there are too many origins, maybe it's because we have just put all the plates together. Fair enough. Other proxies have been like the detrital circons. They just check in the detrital circon record, and obviously the more orogenies you have, especially in subduction zones, in arc geology, you produce more circons. And these circon events, people have said like, well, yeah, just previously to the formation of a supercontinent, we are just getting rid of a lot of oceans, and then we are producing a lot of circons. So basically, these larger peaks in production of detrital circons should represent the formation of supercontinents, or at least very large continents, which I agree. But still, as a proxy, we don't know, and so people have argued that there might be some sort of bias in this record. It's true, there might be some, but the thing that the records are pretty stable around different continents and around different kind of rocks, and like worldwide or even sample-wise, makes people think that, yeah, if there might be a bias, but maybe it's not that big. So yeah, we have these proxy as saying like we may have formed several superplates at some moment. With these kind of proxies, like isotopic or just number of orogenies or large igneous provinces, people have just you know, said there is a series of supercontinents besides Pangaea that, you know, it's known because we can just then do the plate tectonics. So starting with some people, and I'm not going to enter in terminology, I would say later why, but like Ur or some other names for these primordial continental crust. Well, this is just the obviously this is not a reconstruction, it's just imaginary, but something like that, you know, I don't know if that would be a supercontinent. It's too early, and probably was just the first or one of the first large proofs of continental crust on the Earth. Then people say like Knorland, that probably was really more like something closer to a supercontinent at some moment, or a large continent at least. Then Columbia Nuna, that probably is the first one that we can really say, yeah, maybe there was a supercontinent at that time, that in the sense of Pangaea style or something like that. But we know so little about Columbia Nuna that we still fight about the name, which, well, maybe it's not the best thing to fight when you know so little about something. Then it came Rodinia. Rodinia, we know something else. It's not as Pangaea, but it looks like the proofs are kinematically. I'm not just talking about, yeah, there is a peak in the trial circuits, but like we have some good kinematic proofs from the formation, from paleomagnetism, that, you know, we can really reconstruct a little bit better the supercontinent, even if there are some disagreements. Then Pangaea. I'm not going to enter in this discussion. Definitely there was a large continent there. If it is super or not, then probably we need to think about the definition of super for that. But there was a large continent at some moment that called Pangaea, Greater Gondwana, or whatever you want. And then the latest supercontinent that probably is Pangaea, that formed sometime at 320 or something like that, and broke apart 180 in the Jurassic. It was already not anymore. So there are some proxies also, in addition to the zircons or the number of orogenies or the hafnium record, that are mostly Pangaea only, or Pangaea and Gondwana only. And this is like, for example, the curves in the sea level based on strontium isotopes or neodymium isotopes, or the geomagnetic scale that has some, you know, some people has linked that supercontinent with supercrones, but that is only works for Pangaea. Like the formation just fits with one supercrone and the breakup with another supercrone. But that fits only for Pangaea because our polarity scale is just a phanerozoic scale. And in fact, it's basically a Mesozoic and Cenozoic scale, because the Paleozoic is, well, all this gray area in the figure that we don't know. And yeah, the climate or sea level curves are, yeah, basically valid for Pangaea, maybe Gondwana too. So those are all proxies that we can use only for the one that we know, and not really for the others, but we tend to extrapolate. So we know that, so probably it happened before. And then we said, like, there is a glaciation or snowball Earth, and then maybe it is because of that or the other. But still, we are just projecting on what we have seen for Pangaea to the other ones. And I will go back to Pangaea later and to say that maybe it's not valid what we see for Pangaea to other supercontinents. So going to the supercontinent cycle, what people think about the supercontinent cycle, and well, maybe I also think that, or maybe this is what I think about the supercontinent cycle, not really sure, but is that, you know, as I said, continents are just wandering around the Earth, and they get together into a superplate or something that looks like a superplate, the majority of the continents, and then they separate after a tenure that sometimes is, people think like about 100 million years or a little bit more. It depends on the supercontinent. But very importantly, people has used the supercontinent cycle as a geodynamic cycle. And this is key because it's not the same just thinking that you know, the supercontinents form because they can. You know, like plates are wandering, and every now and then they form a supercontinent, and then they break up and keep on wandering. If that was the case, there, yeah, it could be a cycle, but it wouldn't have any, besides the climate trends or sea level. So besides the very surface of the Earth, that concept would be just meaningless for geodynamics. Because yeah, they just get together because they can. So people thought maybe they are not just getting together because they can, or just because if you move randomly pieces every now and then they will get together, but because they are forced to, because the Earth works this way, because the Earth makes supercontinents, and the supercontinents break up because the Earth works that way. Either if it is the supercontinent, the cause, or the consequence of that. So maybe it's the supercontinent cycle which drives the geodynamics, or maybe it's the opposite. But what people think is that it is not just, you know, casual. It is not just something that happens casually, but something that is a little bit driven by the dynamic of the Earth. So the idea would be that people think that either when you form a superplate because of isolation of the mantle, or because it's surrounded by subduction zones that act like a curtain and fit the mantle with new material, but it produces like hot areas, really hot areas in the mantle that will trigger the breakup of the supercontinent sooner or later, or will produce superplumes or something like that. And then start again. Once it breaks up, it starts again, separating in the areas that you have produced these large upwellings to get together in the other side. There are different things, or at least people think that there are different things to form supercontinents, and this is from the same paper of the definition that I did with Damien, Brendan, and Chris. And you know, the classical idea that maybe supercontinents form in the new oceans that form after the breakup of the supercontinent. That usually is the case of Pangaea, and it's called introversion. So you just close the new oceans, or you close the old oceans, like forming a supercontinent closing the Pacific right now would be that case, and it would be extroversion. There is this third option, orthoversion, that Ross Mitchell coined some time ago, which in the kinematic terms is exactly the same as extroversion, but in dynamic sense it's not. So technically, if you just think about the continents moving, it doesn't really matter if they go one way or the other, but for the dynamics of the Earth, it might have some influence. This has also some implications. Is like, why is the role of these new oceans that usually would be, or in a classical view, more difficult to close than all oceans, because it would be, you know, more buoyant or more difficult to subduct, unless there are some other geodynamic forces that force these oceans to close, obviously. And then there is all these coming back to the influence on large plumes or super plumes, influence on, and I could play the GIF that it's from Sane Kotar paper 2016, that they just mapped these large low shear velocity provinces, is that these large low shear velocity provinces that fit with the active hotspots, at least the, you know, the surroundings. So it comes back to the supercontinent cycle, especially because, you know, like this one here, that Torsvik called Tuzo or Jason, or I don't know, one of those. That kind of fits with the shape of Pangaea, and the other one kind of fits with the shape of Rodinia, or this is what we think. And then it's evoking, like, yeah, maybe it's because the subcontinent forms on top, and then all these subduction zone goes there, and you can just fit them with new material, and all the plumes come there. So, and maybe these change, or maybe these do not change that much, and there is a lot of ideas about them. And in fact, the idea of and this is just from, it's a new drawing I did from Torsvik papers. This group from Oslo, what they think is that they are kind of fixed. they are there, and the Earth is simple. They have just two big upwellings that has been there at least 500 million years, but probably all the history of the Earth. But other people think these are changing, evolving, and they depend on the supercontinent, or where you form large masses that have large subduction zones. The fact is that we don't really know, but it's a compelling evidence that is there. It's like, what is that, and why looks similar to the shape of the supercontinent? These areas are, because I'm just saying what it is, just for the people. Probably I've seen the names there, so everybody knows much better than me what those areas are. But anyway, these areas are areas that the waves go a little bit slower, and that have probably a different chemistry, and definitely a different temperature. And that, yeah, as I said, like hotspots apparently come from there. There are different ideas about how these hotspots come from there, and some says like they just come from the edges of that, from the 1%. That is the idea of Orkey and Torsvik and everything. Other people think that no, but it's a continent right now, but they might be also from the center of them sometimes, or maybe it's just a big dome. It doesn't really matter that much. Plumes apparently comes from there. So we have like right now two big antipodal or close to antipodal things that have upwellings from the deep mantle, and and they might be related or not with the supercontinent. And then we go to the idea of if the supercontinent is what is driving this. So it is the fate of plate tectonics that just making all these slabs going down and then feeding the mantle to produce upwellings that will keep the fueling to the big idea of the supercontinent cycle. Or is the other way around? It's just mantle dynamics forcing the formation of supercontinents, because there are two large upwellings or one large upwelling that transform into two or into three every now and then, but that the supercontinent has nothing to do with it. It's just a consequence, but it's not touching the geodynamics itself. It's just one of the other consequences. And yeah, or we can just go to the Torsvik idea that no, those are just independent features. They just move things up and down, and plate tectonics goes a little bit in another level. So those are two different things. And then we can use them following Torsvik for paleolongitudes, which that is why he likes them fixed. It's because he can fit the plates in the ways he likes into a paleolongitude. So going to Pangaea after this rather long introduction of my questions about the supercontinents, and coming back to the Pangaea CD. Pangaea is what we think the latest supercontinent. We know that Pangaea existed because we can undo the ocean floor, and this is a map with the ages based on the magnetic anomalies. This is from the group of Sydney from the Earth bite, but well, we have known that almost since the beginning. Some people didn't want to believe at the time, but he was pretty good at saying, like, in the Carboniferous, these things were together already, and they were by the Eocene, they were already separated. So it has been more than 100 years since this idea that there was a primordial supercontinent has been there. So yeah, we know it was a very large continent, regardless if it was a superplate or if it had an influence on the mantle. It was a very large continent that existed for some time. But in fact, we know how it was in the Permian, but still there is a big debate on the spatial configuration, how it was, and there is, every now and then there are still papers about if it was Pangaea A and transition to B or not. We don't know if it was a rigid superplate. And in that case, it is like, if it was never a superplate, can we consider that a supercontinent in the sense of the supercontinent cycle? And why today wouldn't be a supercontinent in that case? We don't know. Well, we know some. It's not like it's absolutely clueless, but we are not sure how it formed, and there are still we keep on publishing papers on like the amalgamation of Pangea and this origin or whatever origin. And also we have this idea that, for example, Europeans or Americans tend to think like Pangea formed at 320, which is, you know, the age of basically the Variscan-Alleghanian origins or something like that. But then you go to Asia and no, Pangea is, you know, it's late Permian, early Triassic, because until Asia is not part of Pangea, it's not Pangea. So it's also a part of a view. When supercontinent is a supercontinent, when your country is amalgamated into it, or when it's big enough, or a plate or whatever. And why it formed? Because apparently it formed, well, apparently it formed over a large low shear velocity province, unless that large low shear was not there at that time. But like the proofs or what we know so far, it looks like it was there. So it forms over a large upwelling, which is a little bit counterintuitive, that, you know, continents get together in a place that the mantle is trying to push the other way. And as a kinematic problem, which is the Pangea A and B, so just giving a little bit aside the implications that they should have for the mantle geodynamics, majority of the geology community has this assumption that, you know, 320 million years ago, Pangea was a rigid supercontinent, mostly. Yeah, with some whatever here or there, small problem here, but kind of weird, it's clear. Well, paleomagnetists have this friendly fight for 40 years in which the paleomagnetic poles do not feed, and there should be some Pangea B, and there are super mega shear, and that transform into that for geologists, this for classical geologists, that's alive. There are not such a thing. In my case, since I come from both communities, from the geology community and the structural geology, and then I became also some sort of paleomagnetist too. So this is a very interesting topic, because, like, you know, there should be something. So the idea of the paleomagnetist, or not all of them, but many paleomagnetists, is that the poles do not fit. So there is a large problem in that continents overlapped. And that would be kind of the classical overlap here. This is from my friend Matt Dumayer's paper in 2012. And this large overlap between continents, some paleomagnetists suggest it can be solved with a big mega shear. So that big mega shear would just could solve the paleomagnetic problem. There wouldn't be any overlap. You just move it during the Permian or early Permian or late Permian, depending on who you follow. You will move the continent like that, and problem solved. The problem is that 3,500 or 4,000 kilometers of shear zone in the middle of a place that has pretty good outcrops, it's hard to hide, but it's pretty hidden, because nobody has seen such a shear zone. There are some shear zones, but not that kind of shear zone. And if we follow the area, that would be a kind of a sketchy map of the area. You know, like, yeah, there are like some shear zone that goes here, but that's not something you really see. So it's a big problem. And the paleomagnetic community, the debate they have is that they said, yeah, some people, the defenders of Pangea, said like no geological evidence, and then they start saying like maybe the problem is that non-dipolar contributions and the magnetic field was not like that, or inclination shallow wind problems, or it was not yet Pangea. That was something that told me somebody. It's like it's Pangea A, because when it's Pangea B, it's not Pangea. So, well, that's a pretty weak argument, but okay. And the defenders of Pangea B said like, yeah, but still it does not fit. So all these reasons you give, it's fine, but the data should fit. So and this is what I have done for some time. I compile all a series of data of paleomagnetism to try to reconstruct that period without following any kind of preconceived idea. So I was not pretending, let's see what happened if it is Pangea B, or if it is Pangea A, how can I fit the data? So like, what happened if I just reconstruct that during the Permian? So I just compile the data, and it's true that the data is not consistent. but not only in paleolatitudes, also in rotations. And it involves a lot of shortening and extension in the core of Pangaea, one way or another. It's impossible to fit. And it's true that it's co-evolved with some like widespread magmatism in Europe or opening of basins elsewhere during the Permian. So it's not as like you expect in a core of a superplate, very stable like Siberia right now. But there was something going on during the Permian. So in Europe, if you just do a very sketchy thing with what it happens with the paleomagnetic data in a very rigid way, it would look something like that. And again, we come into there are overlaps, just the European part, without counting the other overlaps between Laurentia and Gondwana. So there is this problem. And I just reconstructed, and this is from 320 to 270, and then it will go backwards and forward several times. This is with blocks. It will look very blocky, and especially this section here may not make a lot of sense with all these blocks, but then I just use the function of G plates of a deformable plate. So I will explain a little bit how it works. But that would be the situation 320, in which I think Pangaea was still not definitely a superplate, still colliding the continents. There is something here going on. This is a subduction zone having some sort of rollback. That is the subduction of the Paleotethys. And sometime like 270 is when I think Pangaea would be kind of formed in that sense. And now it's going to start the deformable plate. And the blue part is contraction and red part is extension. So yeah, this area with large rollback has a lot of extension. Here there is extension, which is the, oh, sorry. Let's go back. This has less extension, which is where the Permian basins of the North Sea open, and here a lot of extension that is required because otherwise you cannot form these this big space that would be between the southern part of Iberia and Morocco and the counterpart in North America. So if we play it again, and again, don't check too much these blocks, but it's blocky because it was the only way to do it in G plates before the using the deformable plate function. So that would be the idea. So following, this is paleomagnetism plus other geological constraints, obviously. This is how it how I think the final formation of Pangaea would be. So something like a 270 would be when I think it could be considered some sort of rigid. The good thing of my reconstruction right now is that it fits the geology mostly okay. It fits all the poles, but the Adria poles. But let's get the people fighting about Adria, which I don't think they are really good for Gondwana, but that's a different story. But it really fits all the poles, so it ends any possibility of arguing for Pangaea B. But at the same time, it acknowledged the people that believes in Pangaea B that something was happening, that it was not just 320, everything is done, let's move. So in a way, it acknowledged that early idea, but it says, but probably was not that big mega shear, but something else. And as a synthesis in a more cartoon-like, that would be the idea. So at the Carboniferous, there is still some Drake closing. Drake is the ocean that separated Gondwana and Laurussia. There is some Drake closing in that area. We know that because of the deformation ages in North America are younger than in Europe. That would close roughly at the very early Permian, but still Gondwana would be pushing northwards while Laurussia was just moving basically eastwards. So that would produce all the deformation, redeformation in the Variscan belt, and that is there, and that has been there. Well known that there was didn't finish at 320. And that would produce some subduction initiation or rich subduction or something. I don't know, and don't really care that much. It's because the palliative was stable in the reconstruction for some time, which means that if there was a subduction zone, it was kind of the same speed as the reach, and if there was not, it was a very slow spreading. But then it just starts subducting again because you need to get rid of it. And it will end up with the closing of the palliative later, but Pangea being mostly rigid. So concluding ideas. First, about the Pangea part. The layered Carboniferous early Permian or mid-Permian paleomagnetic conundrum is a global paleogeographical problem. It has been, but and our reconstructions fail. We need new ones. My reconstruction said that probably a plate reorganization during the late Carboniferous early Permian can explain that, and it does not require mega shear zones or whatever. And it can explain some of the features that why Pangea broke in some areas that apparently were not suture zones. And finally, that Pangea became a superplate only after 280. So it is not 320, but probably 280, maybe later. And that means that Pangea was between 30 million year and 60 million year a supercontinent. It depends who you really want to follow, because extension started about 220 to 100. So, and maybe it was never one. I don't know. I don't know everything about Pangea. So maybe there are places in which it was still acting. And especially I want to say that if we use Pangea as a case, might not be, but superplates are likely non-stable. So being a superplate probably is much shorter than the tenure of 100 million years or 150 that some people suggest. And coming back to the supercontinents, the supercontinent cycle might be a geodynamic feature, sure, but maybe just a kinematic expression of plate tectonics. We don't know yet. And that it's good because it's good not knowing, because we can do things. So the hypothesis of supercontinent cycle is definitely cool, and I really like it, but it's really infant state. So it's fair to think we know it, but the fact is that we don't. We don't know if it is really a geodynamic cycle, and I think it's also cool not knowing in this case. And we, or at least I, and I have to say I have done it, sometimes given it for granted, and perhaps recklessly. We have used the supercontinent cycle to explain many things, without knowing really what is the supercontinent cycle. And maybe we should go again backwards, like what is really the supercontinent cycle? What is really a supercontinent? And we cannot just explain things with the supercontinent cycle if we are just arguing if Pannotia is a supercontinent or not, because then we have a problem. There are things that we think is a supercontinent cycle that fit with Pannotia, and I notice that they don't. So we first need to be sure that what we are talking about the cycle makes sense to explain things, and not the other way around, because otherwise we end up in a circular reasoning all the time. And last but not least, please, let's agree on the name of the continent of the Nuna and Colombia, because I am just tired of writing double or triple names just to not make people angry. So that's everything about my talk. As you see, many more questions than real answers.